So, in this video, I'm going to solve the following problem for you. Show that the coefficient of volume expansion of a van der Waals gas is beta equals to R times V squared times V minus B all over R times T times V squared minus 2A times V minus B squared. Of course, here R is the universal gas constant, and V is the molar volume, and A and B are parameters in the van der Waals gas, and T is, of course, the absolute temperature. And the second part, what is the expression for beta if A is equal to B equals to 0 for the ideal gas, of course? That would be a good idea if you pause the video at this point and try to solve the problem yourself first. Of course, if you do the calculations correctly, this is what you will get for beta. And then if you do the second part correctly, this is the answer that you will get. Beta will be 1 over T. Okay, now let us solve the problem. So this is the van der Waals equation. Of course, here P is the pressure, A and B are the parameters that helps you to fit this equation to real gases, to the behavior of the real gases. And V is the molar volume, which is defined to be the volume of the gas divided by the number of moles. And of course, R is the universal gas constant, and then T is the temperature. So we want to calculate beta, which is defined to be 1 over capital V times the partial derivative of capital V with respect to the temperature when the pressure is kept constant. But if I use this, V is N times V, little v, and if I put them here, that N that appears here will cancel that N that appears up there, so I can also write it in terms of the molar volume as 1 over little v, the partial derivative of V with respect to the temperature when the pressure is kept constant. Okay, so in order to calculate beta, the ideal scenario is that if you have V as a function of temperature and pressure, then of course it would be a very simple partial differentiation in order to get beta. For example, for the case of an ideal gas, the equation is very simple. It is P times V equals to RT. And then if I want to calculate beta for this gas, I immediately can find V as a function of T and P by dividing by P. And then of course, if I ask what is the partial derivative of V with respect to the temperature when the pressure is kept constant, I see that V is a function of T and P. I want to keep P constant, so this becomes function of only one variable, the temperature, and if I take the derivative, it becomes R over P. But then beta is 1 over V multiplied by that. So if I multiply this by 1 over V, it becomes P times V. And instead of PV, I can plug RT back. R's are canceled, and I get 1 over T. So you see that if you want to calculate this for the ideal gas equation, it is extremely straightforward because you immediately can write V as a function of P and T. But here, if you take a little bit of time, open this pair of brackets and simplify this, you will get a third-degree equation in V. And of course, finding V in terms of P and T in this case would be, if not impossible, it will be formidable and tedious. Okay, so what we want to do, this partial differentiation, but without actually expressing V in terms of P and T. And that's also a famous technique in multivariable calculus. So we do an implicit partial derivative. This will help us without being able to write V explicitly in terms of P and T, this enables us to be able to calculate this. Okay. So I start taking the derivative from both sides of this equation with respect to T, and I remember that I want to keep P constant. But you see that is a product. So I have to use the product rule, meaning the derivative of the first one multiplied by the second one plus the first one multiplied by the derivative of the second. So let us just do that here. So the derivative of the first one with respect to the temperature, when P is kept constant, this P, the derivative of this P will be 0 because P is kept constant, so I have to take the derivative of this part. But if I want to take the derivative of that part, A over V squared, be careful, I want to take the derivative of this, pretending that V is a function of T and P, but P is kept constant, so I can see that V is an only function of T. So if I want to take the derivative of this, so what I do, I can bring this up and just take the derivative of this, so it becomes minus 2a v to the power of minus 3, but by the chain rule, v itself is supposed to be a function of the temperature, so I have to multiply by dv dt. So if I simplify this a little bit, it becomes minus 2a over v cubed, partial derivative of v with respect to the temperature, and let us emphasize that again, we are keeping the pressure constant. Okay, so this is the derivative of the first part, it should be multiplied by the second part. So I will do it here. The derivative of the first part is minus 2a over v cubed, multiplied by the partial derivative of v with respect to the temperature when the pressure is kept constant, multiplied by the second factor itself, plus the first factor itself multiplied by the derivative of the second factor. This is a constant, it becomes 0, and this simply becomes dv dt when p is kept constant. But on the right-hand side, I want to do the same thing. I want to differentiate the right-hand side with respect to the temperature, assuming that p is constant. It doesn't have any relation with p here. R is a constant. The derivative of t, when t itself is assumed to be the variable, becomes just simply 1. So I will have only R on the right-hand side. Okay, but look at the formula of beta. This is the formula of beta. So I want to this manifest itself in that relation. So it motivates me to factor 1 over v dv dt p out. Okay, so I take this out. Here, minus 2a over v squared is left, and of course this factor is also left. And in the second one, this is pulled out. I also pulled 1 over v out, so I have to compensate for that, so I multiply this by v. And the right-hand side is still r. But you see that this is exactly the beta that I am looking for. So I would say that beta becomes r divided by this expression. This becomes r divided by, let me write this one first, v p plus a over v squared minus 2a over v squared v minus b. Okay, so this is the expression that we get for beta. But the formula in the book is not expressed in terms of P and V. If you look at the formula that we are supposed to reach at, we are supposed to write beta in terms of T and V. Okay, so it motivates us to eliminate P in favor of T and V. And that is easy because you see that this expression exactly appears in the van der Waals equation. So if I want to know this, I divide the right-hand side by v minus b, and I plug it here. So if I want to continue, I just write the numerator, and instead of v, I just write v. But instead of this expression, I would write RT divided by v minus b, and then I will copy and paste the second term. Okay, and now my goal is to simplify things a little bit because I want to get rid of these smaller fractions. So I will multiply everything by these factors because I want to get rid of v squared. I want to get rid of v minus b as well. So I will multiply them by the greatest common divisor, multiple, which is this least common multiple, which is this one. So both numerator and the denominator. So if I multiply the numerator by that expression, it simply becomes r v squared v minus b, and in the denominator, when I multiply this here, v minus b and v minus b are gone. I have v squared and a v here, so it gives me v cubed. So I would write RT that I have here multiplied by v cubed. And then when I multiply this here, v squared cancel that v squared, but v minus b multiplied by v minus b gives me v minus b squared. And of course I have minus 2a here as well. And that's exactly the formula that we are supposed to reach at. Okay, so the second part is also easy. The second part is trying to confirm that if the formula goes back, because you know that if in the van der Waals equation, if I put A and B equal to 0, I will get the ideal gas equation back. Okay, and now we want to test if it is working here as well. So in the second part, we just put A equals to B equals to 0. Let us see what this formula predicts for beta. So if B is 0, I will have RV cubed. If both A and B are 0, this term is totally gone. I am left with RTV cubed. And then if you simplify these, you get 1 over T, which is exactly supposed to be. Because if you remember, when I calculated beta for an ideal gas, independent of this calculation, I got 1 over T. And this also confirms that this is also true. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.